everyone. So today we're going to be talking about something called the mean value theorem. So this video is going to be, I think, shorter and hopefully a little bit simpler than yesterday's video, which I know had a lot of different ideas going on in it. So for the mean value theorem, and I'll get into what it actually says in a few minutes, but when you're talking about the mean value theorem, you're always talking about a function that is continuous and differentiable on a particular interval. So I'm just going to sketch some kind of sample function here. So let's say this is a function f of x. So, and let's say that we have two x values here, let's say a, and I'll put b somewhere over here. So what does it mean again for a function to be continuous? It means that there's no vertical asymptotes, there's no holes, there's no jumps. It's just, nice, smooth, or nice continuous graph. You can draw it without lifting up your pen. What does differentiable mean? Well, differentiable means that there's no kind of pointy parts, right? In addition to all the continuous stuff. So if a function has like a cusp or a kind of a corner to it, it's not differentiable. So whenever we're talking about the mean value theorem, we're always talking about functions that are continuous and differentiable between two particular values. So let's say that we looked at our function and we kind of went to the 2 points that corresponded to the endpoints of our interval. So the points on the graph at A and B, and we connect them with a line. So this is something that we actually, this line segment that I just drew, this is something we talked about at the beginning of the quarter, right? And it's a little crooked. I'm going to try to do it better. Not really better, but that's okay. So this is what's called the secant line, right, from A to B. So the secant line from A to B, and that tells you the average rate of change of your function from A to B. If you take the slope of the secant line, that kind of just tells you what's the general trend of your function between those two values. So what does the mean value theorem say? It basically says that if you find that average rate of change between two values on your function, that there has to be some point between those two values where the instantaneous rate of change, or the slope of the tangent line, is the same as the slope of the secant line. So I'm just going to try to kind of eyeball that in this situation. So it looks to me like maybe somewhere over here would work, right? So if I were to find the slope of the tangent line at this point, it looks like the slope is about the same as the slope of that secant line. So I'm going to write down the mean value theorem. And I'm going to write it at first in a way that is going to look kind of like complicated math symbols, but then we'll also write it down in kind of plain English. So the mean value theorem says that, first of all, you have to start off with a function that is continuous and differentiable. Hopefully I'm not going off screen here. Differentiable on the interval from A to B. And so this is where I'm going to first write stuff in kind of math symbols, and then we'll also translate it into plain English in a couple of different ways. So the first thing is that, actually, let me write one more thing here then. So there exists a number C, which is between A and B, such that f prime of C is equal to f of B minus f of A over B minus A. So what is this saying? Well, it's saying that there is some number C that lies between A and B. So in our picture here, if we go down to the x-axis, it looks like c is this number here. So there exists a number c on your interval such that if you take the derivative at c, that's going to be the same as taking, so what is this stuff? This is the slope of the secant line. Or another way of saying that is that it's the average rate of change. So I'm going to write kind of both of those ways of thinking of it down. So one way that you can kind of translate this math stuff into plain English is to say that the slope of the tangent line at x is equal to c is equal to the slope of the secant line from A to B. And a third way of saying this is you can say that the instantaneous rate of change at x is equal to c is going to be the same as the average rate of change from A to B. So basically all the mean value theorem is saying is basically that there exists some number where this happens. So it's saying that if you take any function that is continuous and differentiable and you find that average rate of change between those two values, it's saying that there has to be some number between A and B where that instantaneous rate of change or that slope of the tangent line agrees with the average rate of change. So intuitively, why is this? Well, if you think about it, I mean, the average rate of change is kind of measuring the general trend. So if we look at this function, it goes up, it goes down, but on average, it kind of points in the direction of that purple line. And so it makes sense if you kind of picture all of the different slopes. So if you're going through and drawing all the instantaneous rates of change, it makes sense that those instantaneous rates of change at some point agree with the average rate of change, right? Because they're kind of, at some places they're steeper, at some places they're negative, at some places they're less steep, but on average, their slope should be equal to this line. And so it makes sense that at some point, the slope is actually equal to the slope of that line. One example of kind of how you might think of this in like a real world situation would be the following. So let's say that you go on a 4-hour drive. Let me say it this way. So you travel a total of 200 miles. So what would your average speed be then? And let's say that you're always driving, let's say you're on a highway and it's some really straight, boring highway that just kind of keeps going in a straight line forever. So we're not worrying about going forward or backward. We're just thinking about speed or velocity that's in one direction. So your average speed would be 200 miles over 4 hours. So that would be 50 miles per hour. So, realistically, when you're driving, your speed varies, right? Sometimes you're going, so even, I guess if it's a really empty highway, maybe you could put on cruise control and just actually keep it at the same speed. But let's assume that, it's stop and go traffic. Sometimes you get to go faster, sometimes you get to go slower. So what does the mean value theorem tell us about this situation? It tells us that if your average speed was 50 miles per hour, there must have been, regardless of how much the traffic was stop and go, there must have been at least one moment during your drive where your speedometer said exactly 50 miles per hour. So I'm going to use it frequently, probably in this video, MVT as an abbreviation for the mean value theorem. So the mean value theorem in this situation would tell you that there must have been at least one moment during the 4-hour drive at which your speedometer said exactly 50 miles an hour. So that's kind of an intuitive way to think about what the mean value theorem says. It's basically, that the average, at some point, the actual speed must have agreed with that average. Okay, so we're going to do some examples of basically just verifying the mean value theorem for specific examples. So we're going to look at a few different functions, and we're going to find the average rate of change on an interval, and then we're also going to try to find what's that place where, what's that number C where we actually have that average rate of change equal to, the instantaneous rate of change equal to the average rate of change. So for this first example, we're going to verify the mean value theorem for the function f of x is equal to x squared minus 5x plus 6 on the interval from 1 to 6. So what's the first step in verifying the mean value theorem? Well, basically, we want to figure out what is that average rate of change. And then we're going to try to figure out where is that place where the average rate of change is equal to the instantaneous rate of change. So the first thing we want to find is the average rate of change on the interval from 1 to 6. So that's the same thing as saying, what's the slope of the secant line, basically. So if we look on our graph, here's the point on the graph where we have an x value of 1, and then here's the point on the graph where we have an x value of 6. So this is our secant line. Oops. So if you wanted to find the slope of this line, basically you would want to do f of 6 minus f of 1 over 6 minus 1. And since we have the graph handy, we can just find the values from the graph. But of course, if you were doing this without the graph, then you would want to actually plug the numbers into the function f of x. So f of 6, according to our graph, is equal to 12. F of 1 is equal to 2. So we have 12 minus 2 divided by 6 minus 1 is 5. And so that's 10 over 5, which is 2. So that tells us that the slope of the line we just drew is 2, which looks like it's true. I got a little crooked. It's surprisingly hard to draw straight lines with this sometimes. But yeah, that's our slope. So how do we now figure out at what x value we have this, this same average rate of change as the exact rate of change? Well, if we take the derivative and we set it equal to 2, that will tell us at what x value we have the same rate of change. So what we're going to do is we're going to find f prime of x, and then we're going to solve f prime of x is equal to 2, right? Because that will tell us where our rate of change is equal to 2. So our original function was x squared minus 5x plus 6. So f prime of x is equal to 2x minus 5. And so that means that we're solving 2 is equal to 2x minus 5. So we're solving 7 is equal to 2x. And so we find that x is equal to 7 over 2. So that is the place where that's our value of c. So you could call it x, you could call it c. I'll just write down c to kind of be consistent with how we write down the mean value theorem. So let's try to at least kind of see that that looks reasonable. So where is 7 over 2? 7 over 2 is equal to 3.5. So if we go to 3.5 on our graph, draw a point there, and try to kind of eyeball, and that was not good, but let's see if I can do better, eyeball the slope of the tangent line, you know, it looks reasonable that it should be about the same as the slope of that secant line. Okay, so let's do another example. So basically, I mean, really there's not much in these examples that is really like that new from other stuff we're doing. Like all we're really doing is we're finding an average rate of change, and then we're finding a place where the derivative is equal to a number. And that's something we've been doing all quarter, right? There's been questions all quarter being like, find the x value where the slope is equal to 0, or find the x value where the slope is equal to this. And that's really all we're doing in these problems. Okay, so next one we're going to do is we're going to verify the mean value theorem for g of x is equal to cosine of x on the interval from 0 to pi. So our first step again is we're going to find the average rate of change. So find the average rate of change on the interval from 0 to pi, or the slope of the secant line. So the at x is equal to 0, we have a height of 1. And then at x is equal to pi, we have a height of -1. And so our line looks something like this. Oh, that was not good. Let me try one more time. It's probably like a line tool that I could be using here, but let's just pretend that's a straight line. Okay, so how do we find that slope? Again, we do g of pi minus g of 0 divided by pi minus 0. So what's g of pi? According to our picture, it's -1, or you could figure that out using the unit circle. What is g of 0? So when you plug 0 into cosine, you get 1. So we have -1 minus 1. And then in the bottom, we just have pi. And so altogether, we get -2 over pi. So that is our average rate of change that we're going to try to find. So the next step is to find the derivative. Maybe I'll just write it down here. So we're going to find g prime of x and set it equal to -2 over pi. So what's the derivative of cosine of x? It's negative sine of x. And so we want to solve negative sine of x is equal to -2 over pi. So if we divide both sides by -1, we get sine of x is equal to 2 over pi. And you might look at that and think that, you know, oh, that looks, it has a pi in it. Maybe this is something I can just kind of figure out by hand, but not really, because typically when, you know, if you're doing something with trigonometry, usually the pi is the angle. And in this case, pi is actually the output, right? We're saying sine of an angle is equal to this number. And so 2 over pi, you want to just kind of think of that. Don't think of that as an angle, because it's not. Just think of it as a number. So whatever 2 divided by, you know, approximately 3.14 is, that's what we're trying to find sine equal to. And so the way that you actually want to solve this is using inverse sine. So if we take inverse sine of 2 over pi and type that into a calculator, it is approximately equal to 0.690 radians. And so that is the place where our derivative is equal to -2 over pi. So this tells us that our number c is equal to approximately 0.690 radians. And we can look at the picture and try to verify that. We can't be too exact, but let's think about it. So pi over 2, and I didn't really think of doing this earlier, but let me just type this into a calculator. So pi over 2 would be 1.57. Pi over 4 is 0.78. So pi over, not pi over, our answer, 0.690, is actually around here. It's somewhere like a little bit before pi over 4. So one thing you might notice looking at this picture is that it kind of looks like there should be another place where we have that same slope. So really, in order to verify this, you really only need to find one answer, because like what all the mean value theorem says is that there has to be at least one value where the slope of the tangent line is equal to the slope of the secant line. But let's actually try to find the other one, because I think it's a good kind of practice with working with trigonometry stuff. Okay, so this is actually exactly what we're working on in my 142 class right now, is being able to solve equations, trig equations. So let's try to think about what we just found as a solution. So we just found that if you go to an angle of 0.690 radians approximately, so that would be, like we said, that's a little bit less than pi over 4, right? It's somewhere between 0 and pi over 4. So that means that this angle looks something like this. So this is an angle of about 0.690 radians. So how would you find another angle that has that same sine value, right? Because where did this come from? It came from the fact that we were trying to solve this equation here. So remember that sine is the same as the y-coordinate on the unit circle. So whatever 2 divided by pi is, that number is the y-coordinate of this point. So where could we find another angle that has that same y-coordinate? Well, if we go over here and look at this angle, that's another angle that also has sine equal to 0.690. So how can we find this angle? Well, if we were to measure all the way like this, that would be pi, right? That would be 180 degrees. So if we do pi minus this angle, that will tell us what the orange angle is. And so where's that coming from? Let me just maybe get a little bit more specific. And I'm trying to erase this orange. Oops. It's hard to erase just one thing at once sometimes. So the angle that we found in green here, that's the same as what's over here, right? Because of symmetry. Because these two angles have the same height, they're symmetric about the y-axis. And so that means this blue angle is the same as the green one. And so because if you were to measure this entire thing, that would be pi. If you do the yellow minus the blue, you should get the orange. So the other possibility we have is that C is equal to, or I guess I should say approximately equal to pi minus 0.690. And so that is equal to, and let me just do that real quick because I didn't do that earlier. So pi minus 0.6. So that would be approximately 2.452. Oops, I missed a number here. So 452. So we get two different possibilities. There are two different angles between 0 and pi such that they have that same tangent line. So where would that angle be? Well, just based on our picture here, we can tell that 2.452 radians is, it's between pi over 2 and pi, right? It's getting kind of closer to pi. So if we look at our picture here, that looks like it's going to be somewhere around, maybe here. So if we were to draw the tangent line at this point, it should also have the same slope as the line in purple. So in this case, there are actually two different solutions. So again, in order to just verify that the mean value theorem is true, you really only need to find one. But on your online homework, they ask you to find all solutions, all of the numbers that have the derivative equal to that average slope. So I just wanted to go through that also because I think it's a good review for solving trig equations. All right, we're going to do one more example, and this will actually bring up something a little different. So we'll do one example first that's kind of more normal, I guess, or more similar to the examples we did earlier, and then we'll do a slight variation on it that brings up something interesting. So, even if you feel like you have the hang of it at this point, I would still watch through to the end because there will be something else that will come up. So let's verify the mean value theorem for h of x is equal to 1 over x squared on the interval from 1 to 2. So here's our graph of h of x is equal to 1 over x squared. So the interval from 1 to 2 is going to be from here to here. So we're looking at this secant line. So the first thing we're going to find is the average rate of change on the interval from 1 to 2. So how do we do that? Again, we do h of 2 minus h of 1 divided by 2 minus 1. So what is h of 2? H of 2 is going to be, this one we can't really eyeball, but our function is 1 over x squared. So if we plug in 2 to that, we get 1/4 minus h of 1 is just 1, all divided by 2 minus 1, which is 1. So what is 1/4 minus 1? It's negative 3/4. So that's what we're looking, that's our goal for our instantaneous rate of change. And so our next step is we're going to find h prime of x, and we're going to set it equal to negative 3/4. So if our original function is 1 over x squared, that can be written as x to the negative 2. It's the same as 1 over x squared. And so the derivative is going to be negative 2 x to the negative 3. And for the sake of solving this equation, it's probably going to be nicer to write that as negative 2 over x cubed. Okay, so now we have negative 2 over x cubed is equal to negative 3/4. So we can multiply or divide both sides by negative 1, and we get 2 over x cubed is equal to positive 3/4. And now we can cross multiply, right? So we basically want to get this x cubed out of the denominator so that we can actually solve for it. So if we cross multiply, we get 3x cubed is equal to 8. And so that means that x cubed is equal to 8 over 3. And so last step we can do is take the cube root of both sides, and we get that x is equal to the cube root of 8 over 3, which is the same thing as, so if you take the cube root of 8, that's 2. So we have 2 over, and I should put a cube symbol here. So we have 2 over the cube root of 3. And if you type that into a calculator, that is approximately 1.387. And so that tells us that our number C is equal to 2 over the cube root of 3. So going back up to our picture, so we had 1.387, so that means that that slope is going to happen somewhere a little closer to 1 than to 2, so something like maybe here. Okay, so last example I want to do is, and let me actually copy this picture because we're going to use the same function, but I want to bring up something a little different. So the question here is going to be, what happens if we try to verify the mean value theorem on the interval now from -1 to 1. So you might already have an idea of why, this isn't going to work, but let's just go with it and say we're doing it, and we'll basically see that something goes wrong and then try to explain why it went wrong. Okay, so the average rate of change between -1 and 1, we really don't have to do much work here to see that that's 0, right? But let's still write that out. So the average rate of change on the interval from -1 to 1 would be h of 1 minus h of -1 over 1 minus -1. So h of 1 is 1. H of -1 is also 1. So we have 0 over 2, which is 0. So that in and of itself is not a problem, right? It's fine to have a slope equal to 0. But let's see what happens when we try to set our derivative equal to 0. So we already found in the previous question that h prime of x was equal to negative 2 over x cubed. So if we try to set negative 2 over x cubed equal to 0, that has no solution, right? Because the only way that a fraction can be equal to 0 is when its numerator equals 0. And because this fraction has a numerator of negative 2, there's just no way that it's ever going to equal 0. So this has no solution. And you can kind of visually see that because when you look at the graph, there's no place between negative 1 and 1 where the slope is equal to 0, right? Because the slopes are like very steep. They're never equal to 0. And actually there's nowhere on this graph, not even out here, where the slope is going to equal 0. The slope is never going to equal 0 on this. It's going to flatten out the more it goes this way, but it's never going to actually be horizontal. So did we just disprove the mean value theorem, right? Like when something is called a theorem, it's because it's been proved by mathematicians. It's a legitimate thing. It's a fact. It's something that is always true. So did we just disprove it? No, there's a problem with the function we chose. So if we go back to the mean value theorem, notice that we started by saying if f of x is continuous and differentiable on an interval. So if we go back to this example that we were just looking at, this function is not continuous from negative 1 to 1, right? It has a vertical asymptote between negative 1 and 1. So it was okay for this other example we did because this function is continuous and differentiable between 1 and 2, but it's not continuous and differentiable between negative 1 and 1. And so basically the problem is that if it's not, if the graph, like let's say the graph was nice and continuous between negative 1 and 1, well then it would probably have to go like this, right? And then there would be a place where there was a slope of 0. But because we have a vertical asymptote, the graph can go up and kind of never come back down. If it were to come back down, then this would have worked. But because it's kind of these two separate pieces, the mean value theorem just kind of falls apart. So I'll just kind of write that down. This does not contradict the mean value theorem. The mean value theorem assumes that the function is continuous and differentiable on an interval AB. And what we saw is that h of x is equal to 1 over x squared is not continuous or differentiable on the interval from negative 1 to 1. So that's it for today. And today's worksheet is basically just kind of practicing similar examples to this, and then one kind of bonus problem that is like an application of the mean value theorem. All right, I will see you all next time.